Good morning, thank you for having us. My name is Todd Wagner, and I am the Project Manager and Water Resources Engineer with Vector Associates. Today, the team is here to discuss our final progress on the Crown Point Business Park. In order to communicate this progress, today's discussion is broken up into a few parts. First, I'm going to remind us what we're actually building here, so I'm going to give a brief project overview. Then each one of our engineers is going to have a chance to talk about what they designed individually. And finally, we're going to have a period for questions at the end. So, we've been tasked with designing a 51-acre agricultural lot in Crown Point, Indiana. And the client is a private client who requested 4 different pieces of infrastructure on the site. First, the client requested a roadway to connect Maryville Road to North Indiana Ave or East Summit Street. Then the client requested that that roadway have adequate drainage. And then we've been tasked with developing a 4-acre parcel. And on this parcel, we have a multi-use structure and water resources engineering for that parcel. I'd now like to hand it off to our transportation engineer, Leah.
Thank you, Todd. My name is Leah, and I am the transportation engineer here at Vector Associates. To remind everyone of what I completed last semester, which is what we are calling Phase 1, I designed a connector roadway from North Indiana Avenue to Maryville Road, and I also looked at the intersection of Indiana Avenue and Summit Street and looked at the traffic flow to configure how it will look when everything in the park site has been developed. This past semester, so Phase 2, I have created the profile as well as a parking lot, signage, and a detour route for my road, as well as finalize my cost estimate. So looking at the overview aerial of our site again, you can see our chosen alignment. It is indicated in orange and it follows an S shape. It is just over 1/3 of a mile long at 3.36 miles long, has a design speed of 30 miles per hour, and both of the curves are 275 feet in radius, and which is just over the NDOT threshold of 250 for a 30 mile per hour design curve. The other thing, so if this is now an aerial, we're going to zoom into this southeast intersection right now. And this is of Indiana Avenue and East Summit Street. Previously marked, every approach had a right turn lane and a through and left lane combined. Nope, it had a, sorry, my bad. It had a left lane and a left turn lane and then a right and through lane. I have decided to separate all 3 of those, so there'll be 3 lanes, a left turn lane, a through lane, and a right lane. This allows for a level of service C when the additional trips of over 700 are come into play when all the site has been developed. Now we're going to we're going to go back to the alignment, and we're going to cut perpendicular to the travel lanes and look at the typical section. Our typical section has 12 feet wide travel lanes, 1 in each direction with 2% slope to allow drainage off the road into like the shoulder and grass area. 8 feet from that shoulder, there is a 5-foot wide sidewalk. This sidewalk is all in accordance with the City of Crown Point design standards, and that 8 feet gap of space, which is probably going to be, with grass, will be allow for drainage and drainage facilities for the environmental engineer to infrastructure. If we're going to look also at the profile creation of our alignment, you'll notice there's only about a 6 feet difference in elevation, and there's 2 sag points and 1 crest point. The sag points are here, and then there's a crest point over here. Our environmental engineer, Maddie, will talk a little bit more about that later when she talks about how she implemented grade inlets. So now we're going to look at the chosen parcel of our alignment. Our alignment this time is indicated in black, and we have chosen the parcel in the northwest area of our site. This parcel is just under 4 acres, and we previously had a parcel of just under 2 acres. But when we looked at how many parking spots we would need and everything that would need to go on that site, we realized we would need a lot more land. So we had to come up with 3 options, and our 3 options were to either acquire more property to construct an above or underground parking structure, and or ask the City of Crown Point for a parking lot spot exemption. We actually went with the acquire of our property, so we actually have a double parcel, which is 4 acres in size. Now we're going to zoom into that parcel even further, and we're going to look at the layout of what has been placed onto this parcel. So I'm now noticing that the sidewalk did not come through. But this is the sidewalk, which is what this arrow is pointing to. There's 193 parking spots, which is the exact number needed by the zoning ordinances. And there's also 6 ADA spots, which are indicated in these blue and white rectangles that allow for proper aisle space for van accessible parking as well. And you'll notice here that there's 2 entrances and exits to the parking lot to allow for 2-way traffic throughout the parking lot, as well as 90-degree parking spots to allow for you can approach it any direction. One of the other things I developed this past semester was a detour route. So when the construction of East Summit Street and North Indiana Avenue takes place, which is right here, they will not be able to travel through that. So what would be the appropriate route to take? For people going northbound, I said they could go up Maryville Road to Center Cross Road and down Madison Street, and people going southbound, or sorry, not southbound, if they're going westbound or eastbound. And then they can go Broadway to North Street to North Main Street. And the reason these roads were selected is because then they're just straight paths instead of having to like zigzag all throughout and not trying to interrupt too many civilians in their subdivisions. Our final construction cost estimate for the transportation design actually follows the rule of thumb, which is every mile of an alignment is $1 million. So if you remember that our alignment was 0.36 miles long, this is a pretty spot-on estimate of $360,000. These are rounded to the nearest 5,000 for this presentation. Our intersection layout will be $280,000, and our parking lot will be the most cost-effective at $60,000, making the transportation cost just about $700,000. I'd now like to turn it over to Maddie to talk more about the environmental infrastructure on our roadway.
Thank you. My name is Maddie, and I am the environmental engineer here at Factor Associates. My scope for the Crown Point Business Park development was to create pavement drainage along Via's roadway. This is to ensure vehicle safety during design storm events, and it includes both collection and conveyance components that I will discuss. To ensure that my design is compliant with Crown Point standards, I also was required to do hydraulic modeling, which I will also talk about. So this is an overview of the road that Leah has made with my infrastructure included with it. The first thing I'd like to talk about are the great inlets that I selected from last semester's alternatives. So those are in the green boxes that you can see along the road. I first calculated what the runoff into each inlet would be. I'm working under 2 assumptions. One, that the road and the road right-of-way are the only contributing areas into these grades, and that the ground of the road creates a drainage divide. So that is why you see inlets on both sides of the road and not just on one side. I started at any high point along the road, so this is at the crest of the road that Leah spoke about, and then each end of the alignment are also high points. And from there, I placed inlets so that the spread of water across the road and the depth of ponding at the gutter are minimized and make sure they can comply with Crown Point standards. Then at sag points, I actually included multiple inlets. Because great inlets are prone to clogging and sag inlets have more water flowing through them, this required multiple inlets to be placed at those locations. And so you can see that there. The next part of my design was placing manholes and a concrete sewer pipeline underneath the road. So manholes are placed anywhere where the diameter, slope, or horizontal direction change for the sewer pipe. Because this road curves so much, the change in direction was what really dictated where my manholes were placed. Then at each segment of pipe, the slope and diameter are chosen so that the water velocity is not too low or too high, and to make sure that the energy and hydraulic grade lines are adequate throughout the road. Then at the southernmost sag point is also the convergence of the sewer pipeline. So as water flows through this point, it will be directed off of the road and into the site's overall stormwater management. This is a manufacturer's drawing of the grate inlet that I selected. It follows Crown Point standards. As you can see, there are slots and bars on the grate. This prevents big trash from getting into the sewer pipe itself, but this is why there is clogging that is prone to happen with these grates because it will get stuck on them. And this is the standard drawing from Crown Point's technical standards of the manholes. So they are eccentric cones with a 4-foot inside diameter to allow for adequate space during maintenance and inspections. For my hydraulic modeling, I did attempt to use PC Swim. However, I learned that the program actually uses different design equations than what the HEC 22 standard uses. So the results from that modeling were inconclusive and I was not able to compare them to my own design. However, Civil 3D does have an analyze gravity network command that does use the same equations, so I was able to use that in my modeling. As you can see, there are a couple of pipe diameters that changed, so mostly they increased, and then all of the pipe slopes also increased because I realized that the hydraulic grade line in my pipes was above the crown of the pipe, and during the storm event, this creates surcharging and a pressure buildup that you don't want in a gravity flow network. So by increasing the diameters and the pipe slopes, it lowers the hydraulic grade line and allows for a more adequate design. Then finally, I did a cost estimate of all of the construction, including the inlets and the grates and the inlet boxes, as well as the manholes, which are made of precast concrete, the sewer pipes, and the trenching and backfill needed to install the sewer system. And my total cost came to around $270,000. So I would now like to hand it off to Emma to talk about our structural infrastructure. Thank you.
I'm Emma Hickey and I'm a structural engineer here at Vector Associates. For my scope, I designed a mixed-use steel structure that is 40,000 square feet. I decided the location of the columns, the beams, and the girders to then focus on the gravity and the lateral loads. And then finally, I took a look at the connections and then produced a cost estimate. So here's my final 3D model of the structure. As you can see, it is 2 levels, with each level being 14 feet high. The first floor is for commercial or retail use, and then the second floor is for office use. These were taken into consideration when talking about the live loads. Now looking at the structural layout of the first floor, like the floor holding up the office, W-beams were used for all columns, beams, and girders, and they are listed all right here. As you can see, they are a bit bigger, but that's because they had to hold up the live load of the office, which was 50 PSF, and the dead load of the concrete deck that was added on top of it, which was about 72 PSF. And as mentioned before, there are still spaces left open here for the stairs and elevators. Now this is the structural layout of the roof plan. An 18-gauge metal deck was added on top of this, and W-beams were used again. But listed again, they are much smaller because it only had to hold up the snow load of about 31.5 PSF. Now looking at the structural bracing for the lateral loads, ASCE hazard tool was used to find the wind and the seismic loads. I chose to do diagonal bracing with C-shapes or channels because they were easier to connect to the column, they were more cost effective, and they allowed for a little bit of a drift. The maximum allowable deflection for this structure was 0.4 inches. When I initially looked at W-beams, they had a deflection of basically 0, so that means they were an over-design. And with the C-shape, the maximum deflection that occurred was 0.13 inches, so still well below the requirement. And now looking at connections, I designed 3 typical connections, a girder to column, a beam to girder, and then a bracing to column. I'm only showing one of the connections. This is the typical beam to girder connection, but I followed the same process to design all 3, which was taking the largest shear force or the largest axial force
and dividing it by the nominal strength of the bolt. So for this one, I had chosen a bolt size of 3/4 inches in diameter, and that meant I needed 3 bolts to hold up the shear force of 86 kips. And as you can see, there is a 1.5 inch coping to this one so that the beam and the girder fit together. And now finally, I produced a cost estimate using RS means. When only looking at the material of the framework, labor, and the equipment, the cost estimate came to be $2.3 million. This table lists every single W-shape used and the decks, and that's why it is only $2.3 million. This is my cost estimate from last semester using RS means square footage. So this is the structure as built. So that means it includes all of the finishings, like the doors, windows, the HVAC system. This one also includes like excavation and grading costs. So that's why this one is a bit more at $7.7 million. And that is all. So now I'd like to hand it off to our water resources engineer.
Thank you, Emma. All right. So for the water resources portion of the design, the client requested 3 different things. First, I must control the flood volume on the parcel. Next, I must treat that water, and specifically the client requested that I reduce nitrogen by 60% and reduce total spent solids by 80%. And finally, I must find a way to infiltrate 1 inch of that runoff water. The way I chose to go about these is by utilizing water resources best management practices. So my first set of BMPs were designed to control the flood volume. The water drains from the left to the right on the site. So I placed a vegetated swale to convey water to the design point. To design this swale, I utilized the rational method and the Manning's equation. The next facility was the wet detention basin, which stores that water and releases it at a specific rate. So let's take a closer look at these facilities and the actual results of their designs. So for the wet detention basin, I utilized an inflow hydrograph with the trapezoidal method as specified in the Crown Point manual. And then I sized an orifice structure using iteration and rechecking my work to design a structure that has a maximum allowable outflow of 0.58 cubic feet per second, when the standards require that it must be under 0.78 cubic feet per second. So we're good on this design. Taking a look at the cross-section of this wet detention basin, we can see that the design accounts for safety. There's multiple level landings, either underwater or above the water, so if anyone somehow gets past the 6-foot high fence, they won't fall directly to the bottom of the facility. So the vegetated swale, and taking a closer look, this was my final design. It accounts for 1/2 foot of freeboard, and it's pretty wide at 15.5 feet up top. And that was designed to have a larger area so that the flow is slower and it doesn't erode the actual soil. The second set of EMPs were designed to treat the water quality. So if you remember in my previous presentation, the sand filter was actually located behind the structure. However, as a sand filter is designed to remove total spent solids, I figured that placing it behind the structure wasn't its most optimal location. It'd be better off placing it somewhere like this, where it can take all that runoff from the parking lot and really account for all that shaved metal in the parking lot and brake dust and things like that. So I placed a filter strip as a pre-treatment step to remove those larger solids. Next I have the sand filter and then the biofilter. So let's take a closer look at these facilities. On the sand filter, we can see that the sides slope into it, and on top there's a surface layer of gravel, mainly to keep that sand from moving. In between each layer there's geotextile grid, and there's a 4-inch perforated pipe with 10-foot spacing underneath it. So this will capture total spent solids in that filter media. The next was the biofilter, and this features a 2-stage system. So there's a 4-inch perforated pipe with an upturned elbow. And this upturned elbow creates 2 notable zones in the filter media. The lower zone is the anaerobic zone, and the upper zone is the aerobic zone. When water passes through both of these, it expedites the nitrification process and removes nitrogen from the water by turning it into nitrogen gas. So this helps us achieve one of those objectives. And the final set of EMPs were designed to infiltrate water. I decided to place permeable pavement in the select parking stalls, which are located at the low points of the parking lot. And the reason that I placed them only in the parking stalls was to reduce the amount of fatigue that actually goes on the pavement. So again, let's take a closer look at the actual permeable pavement cross section. So I have 4 inches of permeable pavement above 3 feet of storage media. Now, because the soil is soil group C/D, it's not going to infiltrate as well. So we want to make sure that any water that is below this pipe is infiltrated. But for larger storm events that might overflow the facility, I did place a 4-inch PVC perforated pipe to discharge that water into the wet detention basin when those larger storm events do occur. So this serves a dual purpose. Finally, I used EPA tables and research documents to research the prices of each of these facilities. These prices varied a lot, so I had to take a wide range of values and sort of average them out using a weighted average based on their surface area size. In the end, I found that my facilities, when you account for contingency, which is like material waste and maybe like they take a little too long in construction, my facilities cost $820,000. Thank you for listening. I would now like to open the floor for questions. Yes.
Okay, Todd.
Yes.
I don't know if I saw that before, but I saw the bottom width of the swale is 9 point something feet,
Yeah.
9.2 feet in there. That land is expensive, and so why do you have that wide of, you're taking lots of land for the swale?
I went through a bunch of different iterations, and to find that the maximum allowable velocity was, I think, 1.9 feet per second, or maybe 0.9. It was 0.9, yeah. In order to get it that way, I needed a really large cross-sectional area, so I just had to do this.
Couldn't you just adjust the slope and make it, so you actually, in this case, change your velocity and use this land? And typically, I would say the reason I'm saying that the typical bottom width of a swale is 2 feet.
Yeah.
You are going way.
This is a wide one, yeah.
Yeah.
So if I could, since we're talking about it, so is that, now is it the velocity 0.9 feet per second?
Yeah, so now the velocity does account for the
Is that for like the 100-year storm event, or is that
Yeah.
for the? Okay.
That was for like, I used a rational method to that design point, and that was the flow I got, and I think it was 4.59 cubic feet per second. So this was the area I needed. But yeah, that is a good point. I could have used a steeper side slope, perhaps I think 2 to 1 was the steepest I could get, because 3 to 1 would actually be more shallow. So yeah.
I think it would be okay also to have the flow for the water quality event to be flowing at 0.9 feet per second.
Okay.
And then the flood control event moving faster.
Okay,
I'm not sure.
so yeah, I designed for the flood control,
Yeah.
but that's a good point.
Yeah.
I probably could have looked at the water quality event, which was definitely a smaller design storm.
Question for Leah. Leah, you mentioned that the alignment cost was, and I did, was more of like a rule of thumb from the dot, from NDOT. So is that your final cost estimate?
Yes, so I mentioned that like the rule of thumb is typically that it's $1 million per mile. I use all NDOT pay items for my cost estimate. I was just pointing out how like the rule of thumb and my NDOT pay item cost estimate actually align, which I thought was, it proves that it's true. I just wanted to point, so I did not use the rule of thumb, I used all NDOT pay items. Yeah.
The most recent, so it's not our estimates, but rather the...
No, it's 2025 NDOT pay items.
Does your cost estimate include the curb and gutter and the sidewalks, everything?
It does, yes.
For the, okay.
Mhm. signage, lighting, sidewalk, pavement, all that.
Seems to be on the low end.
It is on the lower end, yeah, but I mean, this is, the rule of thumb is also for like a 4-lane highway as well. So if we take into account, a sidewalk is very expensive. Sidewalk is, for only being 5 feet wide, it's very expensive. So honestly, for having like a sidewalk on each side and 2 travel lanes, it kind of adds up to be about the same as a 4-lane highway.
Thank you. Maggie, I did not sort of see or hopefully I did not miss that. Where does all of your flow go to?
Yes, I didn't show that just because I have both the inlets and the sewer system on here. So the water on the road will flow into the sag points, so there's a drainage divide here at the high points, and then they will flow into the inlets and then into the sewer pipe.
What sewer pipe?
The sewer pipe is the blue lines.
And then ultimately, where does it go?
My scope was focused on just the road, so I did not design for where it would flow afterwards.
I mean, I'm thinking about, I understand that, that's within your scope, so but let's say where do you want to divert it to? So let's say from the high point, it flows in the 2 directions, to the west and to the east, and then ultimately, I would say you're connecting to the municipal system, or you're connecting to Todd's detention basin or something like that.
Yeah, so eventually, ultimately, the water will all flow into this conversions point here, so that could connect it to these municipal stormwater systems because it's close to Indiana Avenue. If I had designed the sewer system up here, I probably could have had it connected to Todd's drainage basin, but he was also designing for just his parcel and not the overall site.
Thank you. And I have to be fair, I have to ask Emma a question.
Since we're on this slide, though, can I?
Yeah, go ahead.
So the blue is the storm sewer pipe, right?
Yes.
So that should, I mean, there should be little stubs connecting the catch basins across the street, right? Is that?
Yes, I did not draw that.
Okay. And then I was going to ask, when you said it was designed so that the hydraulic and energy gray lines were adequate, I was going to ask, what does adequate mean? But what you said after made me think that it was that there can't be surcharge.
Right.
Is
So
that?
the hydraulic grade line, it says in the standards it should not surcharge. So that's not specific, like that's not saying it can't surcharge.
Yeah.
But I tried to design it so that the hydraulic grade line stayed below the crown of the pipe. And
Okay.
then the energy grade line, you wanted to have 1 foot of freeboard underneath the ground surface. So I designed
At the
for
catch
that.
basins?
Yeah.
Yeah, okay. Thanks.
Okay, Emma, so you saw the cross bracing for the lateral loading in here. Where is the location on the big building? Like,
This is a 3D model, the bracing is,
Okay.
and then they mirror each other, so there's one on each side. And then when I drew it here, this is like the long side and this is the short side.
how did you select those locations? Was it random, or there is sort of a formula?
There was not a formula, but when I put it into RS Means, or not RS Means, RISA, it would give me the deflection, and initially I first tried, and it had I tried these 2 spots, and then I had a deflection of basically 0, so that meant it was an over-design. And I knew I wanted to avoid this spot right here, the 16 feet, because that's where they enter for the stairs and elevators, so I didn't want bracing there, because you want less bracing, so there's more rooms for windows and doors. So it made sense for me to put it in the middle, since I only wanted one of them on each side. And then this one I just chose the 30 feet one, because then they matched each other, and it would be more symmetrical.
Just wondering if you have, so this is a commercial building, so most probably you have an elevator shaft, correct?
Yes. That's in the 16 feet.
So why don't you make use of that for your lateral loading as more of to transport the load, the pathway of the loading to the ground.
Maybe that could be an option, but this is the option that I went with. I think also when I was imagining the 16 feet to enter for the stairs and elevator, like I'm picturing like you walk in and it's like a little like lobby area, and then the elevator's more like on the inside and not on the exterior. So it wouldn't be holding any lateral loads.
Okay, thank you.
Yes.
Thank you for your presentation and all the work you've done this year. It's been good. Well, product comes down this year. You show that connection, the beam to the girder. So it's bolted to the, I don't know which one you want to call it, beam, which one's the girder?
I believe
Which
this one is the beam and this one's the girder.
Okay, so it's bolted to the beam. How is it connected to the girder?
It's bolted to,
With,
what did you say?
I see 3 bolts connecting that plate to the beam. How is it connected to the girder?
Yeah.
I mean, it-
He's asking like
Oh.
how the plate
how is that plate connected
Yes.
to the girder?
Okay, that one's welded.
Oh,
Yeah, sorry. I was confused on your question. I was like, there's only 3 bolts, but yeah.
so it's welded to the girder but bolted to the beam.
Then when I was looking at examples, this is kind of what the example following, so I just continued with that.
Well, it kind of makes sense that at least in the building that you don't have the fatigue things that you might have in the bridge, but you can deliver the beam with that plate connected to it, and just stick it up there and weld it, I guess, right?
yeah, so, jump in, Rob.
Sure.
Now, how did you design those connections? Did you do it manually, or did you use the connection extension that comes with RISA?
I just followed that equation that I was saying, like I took the largest shear force or the largest axial force, and then divided by the nominal strength of the bolt that I chose from the AISC steel manual, and then I just designed like the number of bolts required.
So you know that RISA comes with a connection design.
I do.
It does.
If I had some time, if I had more time, I think I would like to explore all that RISA could do, but this is all I knew as a
Well, that's a good experience, learning experience.
Leah, I have a question for you. I'm sorry to make you talk anymore.
No, it's okay. I actually feel fine. I just have a cough. So.
Okay. It wasn't clear to me during your presentation what the design vehicle was.
Oh, yeah, the design vehicle is for a WV65, so typical semi-truck coming in and out of the, in and out of the parcel.
So, and that's used for the curves? and everything?
Yes, for the cars, yes. Thank you.
All right, thank you.
Any other questions?